Welcome to the QEF channel, where we present our cycling studies in an informal way. In this video, we will examine the extra power required by a bicycle disc brake rotor. For this purpose, we selected a favorite model among competitive cyclists, the Shimano RT-CL900 with a 60 mm diameter. The analysis was conducted using computational fluid dynamics software, based on a CAD model of the rotor. The simulation was simplified to focus only on the rotor, excluding nearby components such as the fork, wheel, and other brake elements. Only one riding condition involving a specific cyclist speed and wind profile was simulated. This helped us to obtain an estimate before engaging in a more exhaustive investigation. The results indicate that the total aerodynamic drag across a pair of rotors amounts to 4 watts, which is a factor worthy of consideration in future research. To understand how the simulation accounts for external wind, we need to define a few parameters. Imagine a cyclist riding a bicycle equipped with a rotor. The cyclist moves forward with a fixed velocity. As a result, they experience an apparent headwind of equal intensity coming from straight ahead, which we call Vg. Now, let's introduce an external wind, Vw, blowing at an angle theta relative to the cyclist's direction of motion. The cyclist faces a combined wind, Vr, inclined at phi, known as the yaw angle in aerodynamics. The yaw angle decreases as the cyclist's velocity increases. This relationship is shown in the sketch. With the same external wind, higher cycling speeds lead to smaller yaw angles. This is a top view of the disc rotor. The bicycle is traveling at a high race speed of 50.4 km per hour. That speed generates a headwind of the same magnitude from the rider's perspective. In addition, we introduce an external crosswind of 18.36 km per hour, blowing perpendicularly to the rider's direction. While not particularly strong, it combines with the headwind to create a relative wind of 53.64 km per hour, arriving at a yaw angle of 20 degrees. Observing the airflow passing through the rotating rotor, a turbulent wake forms at the back aligned with the relative wind direction. What you're seeing here is a slow motion animation. In real time, the rotor is spinning at 382 RPM, which corresponds to the riding speed of 50.4 km per hour. In this side view, you can see air passing through the rotor. If you look closely at the external openings, highlighted by the arrows, you'll notice that the disc is rotating. The spinning rotor into the moving fluid creates a frontal force called the translational drag force, noted as Ft. To find aerodynamic power dissipation, Ft is multiplied by the bicycle velocity. It's important to note that when calculating force, the relative velocity is used. However, when calculating power, the force must be multiplied by the ground velocity, which corresponds to the cyclist's velocity. The rotor is also exposed to a rotational drag moment, noted as m, which resists its spinning motion. In rotational motion, force is replaced by torque, and linear velocity is replaced by angular velocity, denoted as omega. So the power dissipated due to rotational drag is m times omega. From the CFD simulation of a single rotor, we obtained that the translational force equals 0.135 newtons. And to calculate the corresponding power, we multiply this by the velocity. Please note that the ground velocity of 50.4 km per hour converts to 14 meters per second. So, the translational power equals 1.89 watts. Now, the rotational drag moment is 0.0027 newtons per meter. To compute the power dissipation, we first convert the rotor speed from 382 RPM to 40 radians per second. And the rotational power equals 0.11 watt. To obtain the aerodynamic power, we need to sum PT and PR. Thus, the total power dissipated by the aerodynamic forces and moment is 2 watts per rotor, or 4 watts for the 2 rotors on the bicycle. The simulation also showed a significant side force equal to 1.35 newtons, which is 10 times larger than the drag force. This large side force acting on the front wheel generates strong steering moments and could be a concern for maneuverability. This still image shows a new representation of vorticity from a side view. Vortices are colored blue if they rotate clockwise and red if they rotate counterclockwise. If you look closely, you can see a couple of counter-rotating vortices, highlighted by the orange arrows, being created at each external opening in the frontal part of the rotor. This is instead a top view of vortices from the same type of stylization. In addition to the aerodynamic drag, there are also other negative influences of the disc rotor that I will just point out. The rotor's weight increases both the rolling resistance of the tire and the rolling resistance in the wheel bearings. When the bicycle accelerates, 2 additional components must be considered: the power required due to linear acceleration, and since the rotor is rotating, we also need to account for angular acceleration. Finally, when cycling uphill, an additional power requirement arises due to the gravitational effect of lifting weight. This component depends on the vertical velocity, which is Vg multiplied by sine alpha, where alpha is the inclination of the road. If you're interested, you can find more technical details on the CFD simulation on our website. Thanks for listening. Bye.